In this lesson, we're looking at simplifying rational expressions. Here I have a set of polynomial expressions. I have 4, which is a constant monomial. 5 is a constant monomial. X is a monomial that's linear, first degree. Here we have a binomial that's linear, first degree. A binomial that's quadratic, second degree. A binomial that's quadratic, second degree, and a binomial that's linear. When we're talking about a rational expression, we're talking about a ratio of one of these polynomials. For example, we could have 4 over 5, or we could have, let's try one down here, x squared plus 3 over x times x plus 3. And I better put parentheses around this x plus 3. And our last expression will be 2x plus 16 over x squared plus 8. So now, by making a ratio of two polynomials, I have created 3 rational expressions. Let's look at our first rational expression, 4 over 5. This expression is simplified as much as it will ever be. If we look down here, this expression is not. We can simplify it further. Okay, I just moved this up a little bit because I want to write underneath it, I want to point out that we cannot have a 0 in the denominator because that's considered a divide by 0 and that is undefined. So our denominator can never equal 0. That means that x can never equal 0 because if x is equal to 0, this x right here will become 0. This will become 0 plus 3, so this will be 0 times 3, which makes the denominator 0. X cannot also not equal negative 3, because if x is equal to negative 3, this x is negative 3, negative 3 plus 3 is 0, and we end up with a 0 times this x, which is negative 3. We end up with a 0 in the denominator. So these, what you see here, these are our domain restrictions right here. In these expressions, x represents our domain or input, and this is merely saying the domain restrictions tell us that x cannot equal 0 and it cannot equal negative 3 in this rational expression. Let's look at this rational expression. Here, x squared plus 8x cannot equal 0. If I factor that, I can factor out an x, and I have x times x plus 8. And this cannot equal 0, or we'll have a divide by 0 error. This means that this x right here, the first x, cannot equal 0. Otherwise, we'll have a 0 times 8. And our other x, this x right here, cannot equal a negative 8. Because if it's equal to negative 8, we end up with a negative 8 plus 8, which is 0. This becomes 0, and it's multiplied by a negative 8. So here, these are our domain restrictions for our bottom rational expression. Now, let's simplify our rational expressions. Well, 4 over 5 is fully simplified because we can factor 4 into 2 times 2 and 5 to 5 times 1, but nothing will cancel out. How about our next expression? Let's factor the numerator. In the numerator of this expression, we can factor out an x, and it's x times x plus 3. And if I rewrite the denominator, I can see that the denominator is also x times x plus 3. Since the numerator and the denominator are equal to 1, this expression simplifies simply as the number 1. Now let's simplify our bottom rational expression. In the numerator, I can factor out a 2, and I have 2 times x plus 8. If I distribute that 2 back in, that gives me the 2x plus 16. In the denominator, I can factor out an x, and I have x times x plus 8. Okay, now here I can see that x plus 8 in the numerator and x plus 8 in the denominator cancel out because it's all multiplication, and what I'm left with is 2 over x. So this is the simplified expression for our third rational expression. Let's find the domain restrictions for these three rational expressions. In our first rational expression, we want to not have a divide by zero error. Well, that would occur. We would have a divide by zero error if x minus 4 is equal to 0. So we're going to say we want it to not equal 0. And now solving for x by adding 4 to both sides, our domain restriction is that x cannot equal 4. In our next problem, we see that 2x minus 7 is in the denominator, and it cannot equal 0, or our expression will be undefined. So here I'm going to add a 7 to both sides, and I get 2x is not equal to 7, and then I multiply both sides by 1/2, and I get x is not equal to 7 over 2. There's my domain restriction right there. In our last expression, rational expression, we have x squared plus 2x minus 3 cannot equal 0. Otherwise, we'll have a divide by zero error. If we factor this into the product of two binomials, we have 3 times 1 is 3, and we need to make the first expression plus and the second minus, and we're going to see that 3 plus a negative 1 is 2, 3 times a negative 1 is negative 3, that's our m and our n, so we factored this. And the zero product property tells us that x plus 3 cannot equal 0, and x minus 1 cannot equal 0, otherwise their product is 0. And on my left-hand side, if I add a negative 3 to both sides, I have x is not equal to negative 3, and on my next expression, if I add 1 to both sides, I have x is not equal to 1. So these are our domain restrictions on our x variable. X is equal to all reals except for these, and when it is equal to any of these restricted values, our original rational expressions will be undefined. Here's a rational expression. Let's simplify it. First, I'm going to change the subtraction to add the opposite, and I'm also going to point out that I have a domain restriction, that is x cannot equal 0. If x does equal 0, then 10 times 0 squared is 0, and we have a divide by zero error in the denominator. Okay, let's keep going with this. In the numerator, I can see I have a 5 here, a 10, and a 35. 5 goes into all of these. And I have an x to the third, x to the second, x to the first. So I'm going to factor out a 5x from the numerator. And when I factor a 5x from the numerator, I end up with a 5x times x squared plus 2x plus a negative 7. I see that I also have a 5x in the denominator. I can factor a 5x out of 10x squared, and what's left is a 2x. Okay, let's move these up. So this is the same expression, but factored. And I see that I can cancel out these two 5x's. So what I have left over then in the numerator is x squared plus 2x plus 7 divided by 2x. And between the numerator and the denominator, there are no common factors, so nothing else can be canceled out. This is my final answer. Some may be tempted to factor the numerator. At this point, if it were factorable, it would factor into two binomials, but I don't see that it's factorable because we need to find two numbers whose sum is 2 and whose product is 7, and that doesn't exist. So this is prime in the numerator, and even if it did factor, it would factor into two binomials, and we don't have a binomial in the denominator. So this is our final answer. Here's another problem, rational expression to simplify. The first thing we know is that there's a domain restriction. X minus 5 cannot equal 0. If I add 5 to both sides, I conclude that x cannot equal 5. So x can equal all values except for 5. Okay, let's move this up. And we can move this up too. And let's start by simplifying the numerator. The numerator is the difference of two squares, and the difference of two squares is the product of two conjugate binomials, which is the square root of the first plus the square root of the second times the square root of the first minus the square root of the second. If you FOIL these two binomials together, you will end up with x squared minus 25. Now let's write the denominator in, and you can see the denominator is x minus 5. Well, this is all multiplication, so the x minus 5's cancel out, and the simplified rational expression is x plus 5. Here's another example of a rational expression that we can simplify. I'm going to change the subtraction to add the opposite so that it's all addition. Then I'm going to rewrite it. Let's move this up. In the numerator, when I look at each term, I see that we have a 4, we have a 23, and a 6. Well, 4 is 2 times 2, 6 is 2 times 3, and 2 does not go into 23. Neither does 3. Okay, so I can't really, there's no greatest common factor here, and there's no greatest common factor here. So let's rewrite our numerator. 4x squared plus a negative 23x plus a negative 6. And I want to deal with the denominator. The denominator should have the higher degree term in front, that is, the x, or the negative x. Since it's all addition, I can commute and say that this is equal to a negative x plus 6. Now if I use factoring, let's move these up again. Let's move these up. If I use the factoring that we've already learned, which is the split the middle term and factor by grouping, I will find that the numerator is equal to 4x plus 1 times x minus 6. And in the denominator, if I factor out a negative 1 from the denominator, I have x minus 6. And from this, I see that I can cancel out the x minus 6's. And the negative 1 that I have down here is sort of a floater. This negative 1 can be, the 1 can stay, but the negative sign can go right out front. And I end up with a simplified expression of a negative 4x plus 1, and I can certainly distribute that negative sign in, and it's a negative 4x plus a negative 1. So this is my simplified expression.